gravity. The most familiar, yet perhaps the most mysterious, force in the universe. It holds us to the Earth, guides the planets in their orbits, and shapes the very structure of galaxies. From the smallest grain of sand to the largest star, everything is subject to its relentless pull. For millennia, humanity has sought to understand this fundamental force. Ancient civilizations attributed it to divine powers. Early philosophers like Aristotle attempted to explain it through natural philosophy. But it was Sir Isaac Newton who first provided a mathematical description, a law of universal gravitation that explained the motion of celestial bodies with unprecedented accuracy. Newton's law, F equals G, times the product of two masses divided by the square of the distance between them, revealed gravity as a force of attraction between any two objects with mass, proportional to their masses and inversely proportional to the square of the distance between. This simple equation explained so much, yet it also left much unexplained. Two centuries later, Albert Einstein revolutionized our understanding of gravity. His theory of general relativity depicted gravity not as a force, but as a curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, and objects rolling nearby will follow curved paths. This is analogous to how massive objects warp space-time, influencing the motion of other objects, including light itself. Key in Einstein's theory, confirmed by observations like the bending of starlight during solar eclipses and the gravitational redshift of light, provided a more complete and accurate description of gravity. Yet, it also introduced new complexities. General relativity, a theory of the very large, seemed fundamentally incompatible with quantum mechanics, the theory of the very small. The quantum world, where particles can exist in multiple states at once and are governed by probabilities rather than deterministic laws, presented a stark contrast to the smooth, continuous fabric of space-time, described by general relativity. The quest to reconcile these two pillars of modern physics, to develop a theory of quantum gravity, became one of the greatest challenges in science. Numerous theoretical frameworks have been proposed, from string theory, which posits that fundamental particles are tiny vibrating strings, to loop quantum gravity, which quantizes space-time itself. But as of yet, no single theory has emerged as the definitive answer, capable of uniting gravity with the other fundamental forces of nature. Amidst this backdrop of scientific exploration, one man dared to ask a seemingly simple, yet profoundly challenging question. Could gravity be controlled? His name was Roger Babson, and his vision led to the creation of the Gravity Research Foundation. Founded in 1948, the Gravity Research Foundation was the brainchild of Roger Babson, a successful businessman and inventor with a deep interest in gravity. He envisioned a future where gravity could be harnessed, perhaps even shielded, revolutionizing transportation, energy, and countless other aspects of human life. Babson's foundation established an annual essay competition, inviting scientists, engineers, and thinkers from around the world to explore the mysteries of gravity. The competition quickly became a prominent platform for the exchange of ideas, attracting contributions from some of the most brilliant minds in physics. Early essays grappled with fundamental questions. Bryce DeWitt, a renowned theoretical physicist, highlighted the immense challenges of quantizing the gravitational field. He emphasized the need to develop a consistent quantum theory of gravity, a theory that could seamlessly integrate general relativity with the principles of quantum mechanics. DeWitt's work laid the groundwork for future research, identifying key problems that needed to be addressed. George L. Bates took a more practical approach, imagining a research program aimed at developing a gravity shield. He explored the interaction of gravity with various forms of matter, considering the possibility of blocking or deflecting gravitational rays. While his specific ideas about shielding didn't ultimately prove fruitful, Bates's essay captured the spirit of practical inquiry that initially drove the Foundation's work. Richard Ferrell delved into the theoretical limitations of manipulating gravity. He explained the concept of weak coupling, highlighting the fact that gravity is significantly weaker than other fundamental forces, making it incredibly difficult to influence. He also discussed the absence of sinks for the gravitational field, meaning that there is no counterpart to negative electric charge that could be used to absorb gravity. The essays from this era explored a wide range of possibilities, from the hypothetical existence of negative mass to the search for alternative theories of gravity. They reflected the scientific community's growing awareness of the complexities of gravity and the challenges of achieving any form of gravity control. Decades passed, and our understanding of gravity continued to evolve. Groundbreaking discoveries, such as the detection of gravitational waves, provided further confirmation of Einstein's theory and opened up new avenues for research. But the dream of manipulating gravity, of shielding its effects, or harnessing its power remained elusive. Then, in the 21st century, a new name emerged: Salvatore Cezar Pais. A scientist and engineer with the U.S. Navy, Pais's research delved into the deepest foundations of physics, exploring the connections between gravity, electromagnetism, and quantum mechanics. His work, while initially met with skepticism, has the potential to revolutionize our understanding of gravity and unlock its hidden potential. Pais's central concept is the superforce, a fundamental force of nature that he argues is the source of all other forces. He demonstrates that this superforce is equivalent to the Planck Force, the force that governs the universe at the Planck scale, the smallest possible scale where both quantum mechanics and general relativity are relevant. Pais once said, "The superforce is the Planck force, present in the equations of general relativity." The Planck force, with a magnitude of approximately 10 to the power of 44 newtons, is the strongest force in the universe. It's the force that holds atoms together, that governs the interactions of elementary particles, and that shapes the very fabric of space-time. Pais' work reveals that this force is not confined to the microscopic realm. It's present everywhere, at every point in space and time, at the Planck scale. Pais argues that the superforce is not just another force. It's the source of all forces. It's the force that, by acting on the fabric of space-time, gives rise to energy density and ultimately creates matter itself. Pais once remarked, "The superforce generates energy density and matter." This concept challenges our conventional understanding of the universe. It suggests that matter and energy are not fundamental entities, but rather emergent properties of the superforce acting on the underlying structure of spacetime. Pais' theory also provides a framework for unifying the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. He demonstrates that these forces are not independent entities, but rather different manifestations of the superforce at different energy scales. This unification of forces has been a long-sought goal in physics, and Pais' theory offers a potential solution, albeit one that requires further investigation and validation. But the most revolutionary aspect of Pais' theory is not just the discovery of the superforce, but the realization that it can be engineered. He argues that by precisely controlling the electric permittivity and magnetic permeability of a medium, we can directly manipulate the superforce itself. As Pais puts it, by manipulating permittivity and permeability, we can effectively engineer the superforce. Electric permittivity and magnetic permeability are fundamental properties of materials that determine how they interact with electric and magnetic fields, respectively. Pais' research suggests that by carefully engineering these properties, we can not only control the propagation of electromagnetic waves, but also influence the very fabric of spacetime and, consequently, gravity. This opens up a new realm of possibilities, particularly with the advent of metamaterials, artificially engineered materials with electromagnetic properties not found in nature. Metamaterials have already demonstrated the ability to bend light in unusual ways, creating cloaking devices and other exotic effects. Pais's theory suggests that similar principles could be applied to manipulate gravity. Imagine materials that can selectively shield against gravity, objects that can manipulate their inertia, or even devices that can generate energy directly from the vacuum of space. These are just some of the potential applications of Superforce engineering. Consider the implications for transportation. Vehicles equipped with Superforce manipulating materials could potentially levitate, travel at incredible speeds, or even warp spacetime to achieve faster-than-light travel. Inertial manipulation could revolutionize construction and manufacturing, allowing for the effortless movement of massive objects, and the ability to tap into the zero-point energy of the vacuum could provide a clean and limitless source of power. Of course, these are still largely speculative concepts. Much research and development is needed to translate Pais's theoretical framework into practical technologies. But the potential rewards are so immense that the pursuit is undoubtedly worthwhile. But the implications of Superforce engineering extend beyond civilian applications. The ability to control gravity and inertia could revolutionize military technology, leading to advancements that are both awe-inspiring and potentially unsettling. Imagine aircraft capable of defying gravity, hovering silently, and achieving incredible speeds without the need for conventional engines. Consider the potential for weapons that can manipulate gravity fields, creating localized distortions in spacetime, or even generating powerful gravitational pulses. And what about defense? Superforce-based shields could potentially deflect incoming projectiles, or even render entire military installations invisible to radar. It's no surprise that certain aspects of this research remain classified. The potential impact on national security is simply too significant to be revealed. Governments around the world are undoubtedly exploring the military applications of Superforce technology, seeking to gain a strategic advantage in the 21st century. The secrecy surrounding this research raises important questions. Who controls this technology? How will it be used? What are the ethical implications of wielding such immense power? These are questions that society must grapple with as we venture further into the realm of Superforce engineering. The potential benefits are enormous, but so are the risks. It's crucial that this technology is developed and used responsibly, with careful consideration of its potential consequences. The scientific community has a vital role to play in ensuring that Superforce research is conducted transparently and ethically. Open collaboration and peer review are essential to prevent this powerful technology from falling into the wrong hands. Despite the potential risks, the promise of Superforce engineering is too significant to ignore. The ability to control gravity and harness the energy of the vacuum could usher in a new era of technological advancement, transforming society in profound ways. Imagine cities powered by clean, limitless energy, where transportation is effortless and sustainable. Envision a world where access to resources is no longer a constraint, where poverty and inequality are relics of the past. Superforce technology could also open up new frontiers in space exploration. Imagine spacecraft capable of traversing vast interstellar distances, powered by the very fabric of spacetime. Perhaps one day, we will even be able to colonize other planets, expanding humanity's reach throughout the galaxy. The potential benefits extend to medicine as well. Superforce-based technologies could lead to breakthroughs in diagnostics, treatment, and even regenerative medicine. Imagine therapies that can repair damaged tissues and organs with unprecedented precision, or diagnostic tools that can detect diseases at their earliest stages. The possibilities are virtually limitless. Superforce engineering could accelerate scientific discovery in countless fields, from materials science to biotechnology. It could revolutionize agriculture, manufacturing, and even communication. But the key to unlocking this potential lies in collaboration. Scientists, engineers, policymakers, and the public must work together to ensure that Superforce technology is developed and used responsibly for the benefit of all humanity. The Gravity Research Foundation, from its inception, has been at the forefront of this quest. Its commitment to fostering research and exploration has paved the way for groundbreaking discoveries like the Superforce. Gravity, the force that binds the universe, has been a source of wonder and mystery for centuries. But now, thanks to the pioneering work of the Gravity Research Foundation and the visionaries who have dedicated their lives to understanding it, we stand on the cusp of a new era. The Gravity Research Foundation's legacy is one of curiosity, innovation, and a relentless pursuit of knowledge. As we continue to explore the mysteries of gravity, we can only imagine the incredible possibilities that lie